Hello everyone and welcome to part 2 of the positional encoding. In our last video we established the theoretical part of why we need positional encoding. Today we will leave this analogy behind and we're going to derive the exact math used in the attention all you need paper. We will calculate the vectors for a sample sentence step by step, and we will prove the beautiful linear rotation property. This makes the system very powerful. Okay, let's start by defining our goal mathematically. We have a position, let's say index 3. We need a function that maps this single integer into a vector of size d model. In our model, dimension is 512, so we need 512 unique numbers to represent position 3. Crucially, as we learned in part 1, we want pairs of dimensions to represent waves of different frequencies. Let's look at the variables we need to control this. Okay, to build this formula, we need 4 variables. The first one is the pos. Simply the words place in the sentence or a position. Second, d is the size of the embedding vector, for example 512, and then the I, which tracks which dimension of the vector we are filling, and finally n, tuning parameter, the standard value of 10,000 by the original authors. This n is essentially controls the range of frequencies we will generate. This is the heart of the mechanism. We don't use one formula. We will use 2 alternating formulas for every even dimension. We know it's even by 2i. We know it's odd by 2i plus 1. So if it's even, we will use the sine function, and for the odd, we will use the cosine function. Notice the argument inside the sine and the cosine is the same. So this one is the same as this one. It determines the frequency of the wave for that specific dimension. So let's break down that argument. The magic lies down in the denominator, n to the power of 2i divided by d. So this denominator, this one. When I is 0, so the first dimension, the power is 0. So the denominator is 1. The wavelength is tiny, just 2 pi. This one. The wavelength becomes huge. This creates, it becomes huge as I gets larger and larger. This creates a geometric progression of wavelengths from 2 pi to 20,000 pi. So 1000 multiplied by 2 pi. This range ensures that every single dimension oscillates at different speed, creating a unique combination for every position. So let's see this in reality. We will calculate the encoding for the phrase I am a robot. Again, we will assume that every word is a token. To make the math readable, we will set the dimension d to 4. This means each position will have a vector of 4 numbers, and we will set our scalar n to 100. Since d is 4, we have 2 pairs of frequencies. Dimension 0 and 1 will use I0, I1. Dimensions 2 and 3 we will use I is 1. So, first, position 0. The math here is very easy because the numerator is 0. So regardless of the denominator, the argument is 0. So the first one is 0. The sine of 0 is 0. The cosine is 1. Sine. Um, so for position 0, the vector is simply this one. This is our starting vector. So we have 0, 1, 0, 1. Now for the second word, m. For the first two dimensions, so I is 0. The denominator is 1. So we take sine 1 and cosine of 1. This changes rapidly for the last two dimensions where I is equal to 1. The exponent is 2 over 4, which is this one, or 0.5. So the denominator is the, you can say it's the square root of 100, which is 10. We take the sine of 0, 1 and the cosine of 0, 1. And we get these values. Note like that these values are much closer to 0 and 1. So like they are changing slower. So roughly we will get this vector. We calculated this by this one, this by this using this one, and this one using this one. Finally, for the position 2, or I am a robot, look at the first two dimensions. The input jumped from 1 to 2. The cosine flipped from positive to negative. From 0.54 it becomes minus 0.42. This is high frequency. This is the high frequency that we talked about here. Look at the last two dimensions. So these ones are these ones. The input only moved from 0.1 to 0.2 and from 0.99 to 0.98. This cosine barely moved because this is low frequency. If you can check the multi-handed clock analogy from the first video to better understand why the last ones or the ones with a higher or lower frequency change very slowly, and while the others make big changes. Okay, if we stack these vectors that we get our positional matrix. Each row corresponds to each word, and each column corresponds to each dimension. If you look down at the columns, you see the wave tracing like 3 paths. This matrix is what gets added to our word embeddings. So if we want, we can even see a clearer picture from like the last two values are changing very slowly, and the first ones are changing very rapidly or with big jumps. Okay, so now for the elegant part. Why did the authors of the paper chose like sine and cosine functions? Or like why we don't just use random numbers? It's because of the trigonometric addition formulas. We know from high school that sine of x plus y can be simply expressed using the sine and cosine. This means that we know the encoding for the position. We can calculate the position plus k using a linear function. So if we know this variable POS position, we can automatically know or mathematically know whatever other position we need to know, plus k. When we apply those addition formulas to our positional encoding vector, we find that the positional encoding for pos plus k is simply a rotation of PE of position. The rotation matrix you see, this one, depends only on k, so the distance between the words is k. This proves that the model can learn to attend to relative positions, like for example, it's like saying 3 words back or 4 words ahead or something, just by learning this rotation matrix. So it doesn't need to memorize, it just need to learn this rotation matrix. So the goal is to learn the relationship between them. So one final math question. Why do we add this vector to the word embeddings? Because we know, like, finally the input should be the embedding plus the positional encoding. Why just not stick it on the end like we do concatenations? Why are we doing the plus? Because adding keeps the dimensionality stable. So this says parameters and computation. So let's say we have the embedding has 3 values for this vector and 3 values of vector. This is the positional encoding and this is the embedding. If we just concatenate them, we will have 6 dimensions, 1, 2, 3, 4, 5, 6 after adding this one. And if we just use the addition, we will keep having only 3 dimensions. But wouldn't this mess up the word information mathematically? Because the embedding space is high dimension. We used an example of 3 here, but let's say it's more than 512. The word information and the position information tend to live in different subspaces. So adding them allows the model to separate them easily later. So we have now seen the engine under the hood. We know the specific sines and cosines frequency. We create a unique, bounded, and linearly relatable fingerprint for each position. But how do we build this? We will see in the future video how to efficiently code them in Python. So thank you for watching. Please like and subscribe the video.